So it's the last session of the first week. Ioan, it's over to you.
Okay, thank you very much. So we'll start where we left off this morning, and again, please interrupt me if you have any questions. We'll see exactly what we cover in this, how far we can go. But yes, don't hesitate to ask or tell me that you want me to talk about this or that. So I remind you that we were looking at this correspondence between FK percolation and the 6-vertex model. So just to be very clear here, we're looking at FK percolation at the critical point, or at the self-dual point if you wish. It doesn't necessarily, I mean, we're never using the fact that it's critical here. Just the exact value. And we have this sort of correspondence, which unfortunately is not a bijection, between, on the one hand, FK percolation, and on the other hand, 6-vertex configurations. Now I remind you, if you don't want to look at the weights, just the way you do this is you draw the loop representation of FK percolation, you orient the loops, and then you keep the orientation of each edge. And that's how you obtain the 6-vertex configuration, and vice versa. If you want to go this way, what you need to do is to split the vertices into loops. So vertices of type A and B, they're split unambiguously. There's only one way to do it. Whereas vertices of type C, which have two opposite incoming edges, they have two ways of being split. So as you take all the ways of splitting this image, you obtain all the images here, and as you go to the left, you obtain a FK percolation configuration. And these models come with weights. If you put the weights right, you will obtain all the weights here are going to sum up to the same thing as all the weights here, almost. I'm really being a little bit loose on the details, right? And the key point is to have this middle, is to look at this middle model as having a weight that is given by e to the lambda over 2 pi times the total winding. And this you can compute in two different ways. Either you say it's the number of loops going clockwise or anti-clockwise counted with a lambda, and the ones going anti-clockwise with a minus lambda. And then if you do this and you sum over all the orientation, you get this weight here. I mean, this weight here, with q being square root of q being e to the lambda plus e to the minus lambda. So this is how you get from this side to this side. And if you want to get to this side, what you notice is that there's a way to compute this locally by looking at every vertex and seeing what is its contribution. The contribution of these vertices type A and B is just 0 to the winding, so that is coherent with their weight being 1. And the contribution of these vertices, well, that depends on how they're split. Each such vertex can either contribute plus pi or minus pi to the winding, and therefore you put their weights to be this. Okay? And so this whole thing works if you sum all the weights. If you don't sum all the weights, you get a bit into more troubling things. And the crucial observation, I mean, or an observation is lambda depends a bit on q. I mean, more than a bit, but there's a big difference at q equals 4. For q larger than 4, lambda is real. For q smaller than 4, lambda is purely imaginary. And at q equals 4, you get the special value where lambda is equal to 0, which translates to the loops being oriented IID. So only for a lambda larger than 4, you have here a probabilistic model. And actually for q strictly larger than 4, the phase transition is discontinuous, and this can be explained in the fact that here you have a sort of dissymmetry, which is not natural, between choosing lambda or minus lambda. You can choose either of the two. And if lambda is real, that really produces a big dissymmetry between e to the lambda and e to the minus lambda. And the reason behind that is that, I mean, the way that can be explained is the fact that actually loops here are very few in number somehow. Anyway, I'm not going to get into that. Those of you who have seen the proof of discontinuity via the Ray and Spinka method, they harness this kind of dissymmetry. Whereas when lambda is either purely imaginary or just zero, the dissymmetry is much smaller here. These two numbers are equal in modulus, it's just one is the conjugate of the other. And this turns out to be coherent with the fact that the phase transition is continuous. Okay. So as I said, from this kind of correspondence, it looks very rich, but if you want to write down something, you don't get so much out of it. You get, for instance, equality of the partition functions, or rather of the free energies. There are some terms here which can be completely ignored. So I didn't put the partition functions, I put the free energies because I cheated a bit in the whole correspondence here. As I said, because you're on a torus, not all loops have a winding of 2 plus or minus 2 pi. So the whole thing is a bit not so precise. But there are error terms coming from boundaries. These get lost when you look at volume effects. So it's much nicer to look at volume. Right. So what can we still obtain out of this? And the idea is to still look at some probabilities here, not just the partition function or the free energy. And here's what I will do. I will define a certain event, which is going to be e to the ek. I'll define it in FK percolation. So ek is the event that there are k red clusters, so k primal clusters, that wind around the torus vertically. The torus is going to be very long vertically, so yeah, just it's basically like a cylinder. You can think about it as a cylinder. So I'm gonna impose ek is the event that there are k primal clusters separate that wind vertically around the torus. This is an extremely unlikely event. I hope this is clear. And we're going to look at how unlikely it is. And it's a very good exercise to think, how unlikely is this event? So just to be clear, if you ask for k clusters to wind vertically, I drew them as paths. They don't need to be. They can have like this. They can have holes in them, stuff like this. But they do need to be separate. So they will be separated by these kind of dual clusters. So dual paths that wind vertically. Even the existence of one such thing is unlikely, let alone of k where k is large. Okay, so how unlikely is it? Let me see if I can. I've written the computation before because I didn't trust myself to do it now. So here are the two versions. In the discontinuous case, it's here. You can actually prove that the probability of this event decreases like exponential to the minus km with a certain constant. C is just going to be a certain constant that can be bounded above and below. So why is this? Well, essentially, in this regime here, the primal and the dual, they really, really, really hate each other. They really dislike being next to each other. So you're basically paying you're paying an exponential for every cluster that wants to exist next to a dual cluster. So you see there are k clusters like this, and each have length m, so you're paying exponential to the k times m. And this is basically optimal. I mean, you can't clearly the event has probability at least of this order, and what I'm telling you is that's also at most of this order, with a value of c here that is not the same in the at least and at most, but it's of this order. Okay, is this something that is convincing? I hope it is. what about in the case of RSW? And the way I like to think about RSW is, I mean, I'm telling you that the probabilities is of more or less this order, with a constancy. I can't prove that the constant here is just exactly a constant, but I can put lower and upper bounds with different constants, but of this type. And the way to think about this is to say, look, I want to create this event. I want to show you that the probability is at least as big. So I want to create this event. I'll just zoom in and show you how to create this event. So I can create this event using crossings. For instance, the red, I can just decide that I'm going to use this area for the red, and I'm going to build crossings of vertical crossings of these rectangles here, and I'm going to connect them as we saw in the RSW picture. Then I'm going to do the same on this side here for the blue, like this, etc. And so what you need to know is how many times do you need to apply RSW to get this? These rectangles here are going to have a size n over k. And so if you work it out, if you do the computation, there are more or less these many rectangles that are involved. And so you're basically doing saying that this is I mean, you're obtaining a bound by saying, look, if I cross all these rectangles the way I want them to be crossed, then I create my event. Okay. Is this something that is convincing? So you'll notice that the probability, the probability below is much larger than the probability above. Yes, because k is always much smaller than n a priori. Okay. So what we'll do is we'll look at this where k is, we'll look at these probabilities where k is alpha n with alpha small. So what I'm saying is I'm going to ask a very high density of such a very large number of such crossings, so much so that it's almost a density, but a very small density. So they're still far away from each other, but the torus is much bigger than the spaces between the two. This space is 1 over alpha, and you're looking at a much larger torus. And if you look at this, the probability of this event is actually computable, or almost computable, in terms of partition functions of the 6-vertex model with a slope. Why is that? Well, let's look at the representation in loops of a configuration of this type. Okay, so how does this look? Well, there are obviously like small loops here, like this, but there are loops that go between the red and the blue. You necessarily need to have these loops that wind around vertically. There are 2k of them. And so now you start orienting all of these loops as you do to get from this side to this. Okay, you start orienting all of these loops. So what you notice is that when you orient any of these small loops here, they'll contribute as many arrows going up as down on every row, because each loop, as many times as it crosses a row upwards, it also crosses it downwards. So these guys are not going to produce any imbalance in the number of up arrows versus down arrows on a horizontal row. The only way to produce unbalances comes from these large loops that maybe you could imagine that there's a positive probability. It's not really a probability because you're working here with complex numbers, but you could imagine there's a positive probability that they're all oriented upwards. I mean, this probability is exponentially small in the number of loops, but this doesn't make any difference if you're looking at the volume effect. And so if these all get oriented upwards, then all of a sudden you obtain here a configuration in the 6-vertex model with n over 2 plus k up arrows per row. And this contributes to zk as it was written. And so if you're taking k to be alpha alpha times n, you get this sort of equality. Okay. There are a lot of boundary terms here, the orientation of the loops and so on, but all of these get lost because you're looking always at the volume effect here. And so when you look at this and you take it, factor this in, you will notice that if I put k to be alpha alpha n here, what you notice is that you expect this probability, I mean, you have that this probability is either of the order of exponential of minus C alpha mn, sorry, C alpha, or exponential of minus C alpha squared. So this is RSW, and this is if phi 0 is different from phi 1. So the question is this difference here of order alpha or alpha squared? If it's of order alpha, that means that the free energy, this function here that is a function of the slope, is non-differentiable at 0, whereas if it's of order alpha squared, it means that this is differentiable at 0. Okay, here alpha is only positive, and clearly the function is symmetric. So if it's the function f as a function of the slope, either behaves like this if you're of order alpha, or behaves like this if you're of order alpha squared. The question is, are you differentiable? Is f differentiable or not at 0? Okay, and so if we want to decide whether f is different, if we want to decide whether we're in this case, or so the discontinuous case or the continuous case, this is going to be immediately given by whether f is differentiable or non-differentiable or at 0. So maybe I'll write it here. Okay. Right. So I'll get in a minute to how this how you solve whether, I mean, you can see if it's differentiable or not at 0. But let me just also say before that our goal, our ultimate goal, is to understand the continuous phase transition. So to understand this regime better. And you remember this heuristic about getting this this cost here for the event. The heuristic was, well, I can produce the event at the cost of order this, or exponential of this, by saying, look, I take all these little rectangles and I cross them and so on. Obviously, this is suboptimal. It's not like this that the event is gonna get created. This is just one way of creating the event, but it will likely be created differently with very high probability. But still, it kind of indicates that the cost of the event, which is this constant here, is related to how you create this event in the most economical way. And it should somehow be related to the probability of crossing a rectangle here. So this constant should encode something about the scaling limit. Okay. I don't know exactly what there. It's hard to relate the constant to something exact in the scaling limit, but it should be something like this. Okay, so at least from a heuristic point of view, if you manage to get this constant, then you basically understood which scaling limit it should be. For instance, if you know that anyway, I'm not going to go more into this, but it is something, if you understand that constant, you do get information about the scaling limit, and morally, you should get all the information about the scaling. And it's the same as this constant here, which is basically the second derivative of the this free energy at slope 0. I don't know what to write here, but basically, if you get the second derivative, you get that constant. There's a factor 2 inside or something, but I'm not gonna get into that. Okay. So I hope this was more or less clear. It's heavy, so it's normal that it's not completely clear, but I hope it was understandable a bit. So now I'm going to show you how to distinguish these two cases, and hopefully also how you compute the constant. So I'm just very briefly going to give you a quick introduction to the transfer matrix formalism. So now we're going to just look at 6 vertex, and we're going to define the transfer matrix of 6 vertex, and we're going to use it to compute the partition functions and the free energies. So what we're going to do is we're going to look at the 6 vertex model row by row, horizontal row by horizontal row, and we're going to look at just the vertical arrows. So we're going to have a matrix that is going to be encoded. It's going to be indexed by potential configurations of vertical arrows. So here's one entrance of the matrix, and here's another. So the line and the column are given by these two things. So it's a 2n by 2n matrix. And the entry corresponding to this is simply you take all the possible ways of drawing here horizontal arrows that obey the ICE rule. Yeah, I don't know, something like this. And you compute the weight of this configurations. So it turns out that this is quite simple. There's only one configuration at most that matches, except in very particular cases. Yeah. And many times this is equal to 0. Side. So oftentimes there's no way to pass from one row of arrows to the next. But still, so if you do this, you obtain a matrix, and if you want to compute the partition function, it's quite clear that the partition function, where am I going to write it here? Maybe z mn is equal to, what you're going to do is you're going to take the transfer matrix to the power m, which corresponds to having m rows of arrows. You're going to sum over all ways of putting these horizontal configurations. And then you're going to impose that the bottom configuration is the same as at the top because you're on a torus. So that corresponds to taking the trace of the matrix to the power m. Okay. So this is what you get out of the transfer matrix. Okay, as such, it's not a huge computation. It's quite easy to see that you would have something like this. What's interesting is that you can understand a little bit more this transfer matrix. So first of all, what can you say about the transfer matrix? Well, as I said, it's a 2n by 2n, a 2 to the n by 2 to the n matrix, but it's actually a matrix that is by blocks. It can be written like this with different blocks, because you can never pass from one line to another if the number of up arrows on the two lines is different. You remember the number of up arrows on every line stays the same. So this means that the actual matrix is split into blocks, each block corresponding to a number of up arrows. So you have here the block T to TK like this, corresponding to K up arrows. And the largest block is obviously TK, not K up arrows, but n over 2 plus K. I want to have T0 as the middle block, which is the block where the number of up and down arrows is the same. It's the largest block. Okay. And so now you can see we're approaching a little bit this idea of looking at finite energies for models with a fixed number of up arrows, because if you have your matrix like this, you can do this same computation block by block, and what you get is that the partition function of the model with k excess up arrows on every row, this is computed in terms of the corresponding block of the partition function by taking the trace of the matrix to the m. And these blocks are all Perron-Frobenius matrices, meaning they have a leading eigenvalue that is unique and an eigenvector corresponding to that eigenvalue that has positive entries. And so if you're computing the trace of the matrix to the power m, if you're diagonalizing it, for instance, you'll notice that it's the largest eigenvalue is going to be the thing that counts. So this is leading eigenvalue of block T. Okay, and it all depends on n, that is the width of the torus, but doesn't depend on m, that is the height of the torus. The only place where we see m is here, and in the fact that there's a correction which is exponentially decreasing in n. Right? So now if you factor this in and you look at the part and you look at the free energy, you kind of understand that you know, this m here is going to disappear as you take the free energy because you're dividing by the volume, and what's going to count is going to be the limit. Oh, sorry. It's going to be the limit as n tends to infinity of 1 over n log lambda alpha n. Okay, it's going to be something like this. So you're going to take the eigenvalue corresponding to a block here that is quite far from the main block, the one with the 0 excess of up arrows. You're going to take a block a bit far away in a matrix of size n, or 2 to the n. You're going to divide this by 1 over log of this by 1. Okay, this is going to be it. So our goal is now to kind of compute these eigenvalues. And there's a way that is quite general to compute eigenvalues of matrices of a certain type. This is something I know very badly, but I learned because of these projects, which is the beta ansatz. So I don't want to go into this computation. I'll basically tell you that the computation works, but I can show you a little bit how it looks, just so that you see it once. Because if you're like me and you never heard about it before, you're going to be a bit surprised at the form. So basically what the beta ansatz tells you is there's a good way of looking at vectors and eigenvalues that are going to have high chances of being the ones that you're looking for. So you're starting off with some numbers here, P1 up to Pn. I'm not telling you what these numbers are. If they satisfy a certain equation, that's called the beta equations, then you can extract from these numbers via this an eigenvector of the matrix. V should be, sorry, V should be T here. It's the matrix. And here's the eigenvalue formula corresponding to it. So you see it's very convoluted. And in the discrete, meaning for a discrete system, trying to solve this, it's quite horrible. And trying to understand this. But there is an expectation that there exists a solution to these equations, and that this solution produces an eigenvector for this procedure here, and that this eigenvector is actually the leading eigenvector of the corresponding block. Why there's an expectation from that, this you need to ask people that know more than I do. And what happens is, under good assumptions or conditions, if you pass now to the limit in volume, meaning this capital N here goes to infinity, everything becomes a continuous and much nicer equation. So this equation becomes a nice equation over the density of these PIs, and this becomes an integral, and you start being able to analyze the limits of these eigenvalues. So here's a more concise form of the statements. In the discrete above, you have the beta equations and the eigenvalues. And below, you have the same thing in the continuum. So if you have a limit, if these PIs start getting distributed as a limiting density, then the density should satisfy this equation, and the eigenvalue is going to be then this. And you see, you're looking exactly at the kind of asymptotic that we had on the previous slide. Okay, so if you manage to do this this passage rigorously, then you're left with trying to solve this equation, which can be done through Fourier analysis. You can solve this equation. And so this is kind of the program of implementing the beta-ansatz computation, but there are a lot of steps here that you need to formalize, namely why there exist solutions to this, why it's unique, why you have condensation, meaning why the solution starts behaving in the limit like a continuum density. So this is the main thing. The second big problem is, why is the resulting eigenvalue that you're computing here really the main eigenvalue? Why is it the leading eigenvalue and it's not just some other eigenvalue? And again, you need to solve this in a certain way. And finally, there's the computational part. Like, if you assume that you do have this as describing the limiting eigenvalue, you need to solve these equations and extract information on this, on the limit of this. Okay, but if you have good friends that know how to do this, as I turned out to have, in our projects, the expert on this is Karol Kozlowski. He knows these things very well. He taught us how to do it. We learned how to do it. And so with his help, we obtained indeed the asymptotic of this thing. And so what we obtained is that indeed, if C is larger than 2, as expected, the eigenvalues here, if you're computing their ratio, which corresponds to computing the increment of the free energy, you obtain an order alpha. So here you obtain F non-differentiable at 0. And if C is between 0 and 2, which corresponds to the regime Q smaller than 4 and more, you obtain a differentiable function. And actually, you can also compute these constants here. I'm saying explicit, it's not, maybe it's a bit exaggerated to say explicit, it's maybe more implicit than explicit, but my point is we show that these constants exist, and we have an expression for them, which we then also manage to obtain more precisely. And so from this, as I explained before, you conclude well the probabilities of these events with many primal and dual crossings either have a probability of this form or of this form, and from this you obtain the conclusion, which is that the phase transition is continuous when Q is smaller than 4 and discontinuous when Q is larger than. So this is the end of the proof of which separates which solves the dichotomy, which tells you when you're in the one case and when you're in the other case. I also mentioned that these constants are relatively explicit, and they are related to things. So this constant here may be used to obtain the correlation length at criticality, meaning you can look for Q larger than 4 at the critical model, and since you have exponential decay for the free measure, you have something called the correlation length, which is the speed of exponential decay, and it's related to this constant. If you manage to compute this constant, you have that. You basically get the correlation length. And here, this constant, which is much more interesting, in the case of continuous phase transition, should be related, as I said, to the scaling limit. And when I say should be related to the scaling limit, to me, the fact that this constant exists and that you can compute it or at least show its existence is already a strong indication that the scaling limit should exist. It's an indication that some sort of discrete object has a limit in the as the mesh size goes to 0 or as the size of your observation window goes to infinity. This is something valuable. Actually, the only time when you had something like this was for Bernoulli percolation, or more generally for FK percolation, when you look at the probability of crossing a square, which this one tends to 1/2. Sorry about that. Simply because it's always equal to 1/2. This is for Bernoulli percolation. If you look in FK, you have a slightly different values. It's a bit more. I'm not going to get into why. It's a different value. But this is somehow an indication that there's something in the limit, but it shouldn't be enough because it's very based on symmetry, this one. The fact that this constant exists to me is more information that there should be something in the limit. And I'm cheating a bit because actually the answer is there is something in the limit, and this constant tells you that there is something in the limit, but I'll try to explain this next week when I'm talking about the 6 vertex conversions to the GFF. Right. Are there any questions about this? Okay. Maybe just to finish, I mentioned that there's some sort of height interpretation of the 6 vertex model. I just wanted to show you this, and very briefly, just like that. So the way you obtain a height from a 6 vertex configuration is quite easy. You start off with a given face where you put just 0 as a height, and as you go to adjacent faces, you have a rule for either incrementing or decreasing your height by 1. So if when you cross an edge, the edge points to your left, then you increase the height. So here I increase the height, that's why I put 1. Here I decrease the height because the edge was pointing to my right, and I put a 0. Okay, so let's follow this rule and fill up the square with heights. And now you're going to tell me, yeah, but I can get from here to here like this or like this. Who guarantees that I get the same height increment? And I'm going to answer the ICE rule. The ICE rule tells you that as you loop around the vertex, the total increment is 0. So if you loop around a number of vertices like this, for instance, the increment is 0, which means that going from here like this or going from like this, you get the same height increment. Okay, so that's why here I could draw these heights correctly. Is this clear? So it's not clear. It's not at all true that I do this correctly. The whole thing works if you're in a planar domain or in a plane, but as soon as you can have loops that are not retractable, you're in trouble. And you will notice here that if you look at a loop that goes like this, the height increment is not well defined, I think, unless I'm mistaken, but anyway, no, it's not. So you have non-trivial height increments as you loop around the torus like this. So unless your configuration has an equal number of up and down arrows on each row, there's no good definition of height on the torus or on the cylinder. You'll pick up a increment as you wind around the torus. And this corresponds to that slope. That's why I mentioned slope, because it's the kind of the total increment. And what you expect is that if you zoom into a piece of this and you have a total slope, you will see it local. Anyway. There's a whole, rather than looking at FK as a percolation model, you can also look at the heights of the 6 vertex and look at this as what's called height function model. So look at the heights, how they vary, etc. And what we've said previously has a direct impact on the heights, and namely, when C is larger than 2, the fact that you have this non-differentiability of F translates to the fact that the heights are localized, which means that if you look at this torus and you don't put any slope, you're just at slope 0, and you make a very, very, very large torus, your heights are still going to be around constant. They're not going to vary at all. The correlation between 2 points will decrease exponentially and so on. There are a lot of different characterizations. Whereas for C smaller than 2, between 1 and 2, the heights are delocalized, meaning in a torus or in a domain with height 0 on the boundary, the height in the middle will have a variance of order log. The correlations will have will decrease algebraically and so on. Anyway. And what you expect, or you can expect it till next week, is that in this case you have a limit of this height function distribution, which is a Gaussian free field. Right. I mentioned, by the way, maybe since nobody's asking, I'm going to ask myself. I mentioned here C smaller than 2, but I also wrote C larger than 1. The larger than 1 shouldn't be important. It's just that some of these things are proved. So this implication here has been proved in 2 different ways. Once by Piet and Alexander Glassman, as I mentioned, and once by Hugo, myself, and Mendes Ulamaha, and Alex Carilla, and I think Dima Krachun. So this has been proved, but the inequality C larger than 1 turns out to be quite crucial, but not for good reasons, I would say. It's just that we want our representations to have FKG, some FKG property, and it only holds for C logic. But normally you expect the whole regime C02 to be in the same sort of have same sort of behavior. All right, let's go to the last section where we will look more precisely at the critical model in the regime Q between 1 and 4, so where you really have criticality. How much time do I have?
Maybe 10 minutes. Is that enough?
Okay. Yeah, I'll just announce a little bit things that are valid here. So my goal was to show you the proof of the theorem in this part, but I obviously will not have time. So I'll just state the theorem, which I will use next week in my talk. And I'm sure that many have seen this, and I'm sure you can find it online if you want. So let's repeat and see what the major conjectures are in the case where P is the self-dual point or the critical point. We know that it's the same now, and Q is between 1 and 4, and so the phase transition is continuous. So here are a few things we know as consequences of RSW, which we know now occurs at these values of Q and P. So as you look at the very large picture, I've taken here a small picture at the top and a much larger picture at the bottom, which is completely it's not a proper simulation. It's a proper simulation of Bernoulli percolation. You have certain features that come out of RSW. Namely, you have in this picture a finite number of macroscopic clusters. If you look at the number of clusters of diameter larger than some threshold, there will be a finite number with an exponentially decreasing tail, or more than exponential, I guess. You have fractal behavior for the boundaries, for the clusters, and so on. Probabilities and probabilities of connections at large distance decay algebraically. You have mixing properties that tell you essentially that the picture here is almost independent of the picture here. And you have all these features that are indicative of scaling, of the existence of a scaling limit. Actually, what you also have is subsequential, I should have written here, subsequential scaling limits. You know that there exist subsequential scaling limits which are non-trivial. I'll explain what that means. And so what are the main conjectures in this setting? Well, you expect that there exists a scaling limit. You expect that the scaling limit exhibits very strong symmetries, namely invariance under conformal transformations. You expect that the scaling limit does depend on Q, again, for Q between 1 and 4. So all of these models are in different universality classes. But what you expect is that for each Q, you have universality, meaning the small scale details of the model are irrelevant to the scaling limit. Now, what are the small scale details of the models? You can't really know because I haven't shown you other models, but you can maybe imagine that you could change the lattice a bit. You could change maybe some, maybe change the graph a little bit lower. One way of changing the graph would be to rotate it. So one question that you have is, okay, maybe there exists a scaling limit. Is this scaling limit the same as if I rotate here by an arbitrary angle? And the answer is yes. Let me just wait just a second. I need to think about how I want to. Okay, I'll just show you the theorem, okay? And then I'll come back to clarify things that are written in the theorem. So the theorem is, yes, you have both universality and you have invariance under rotations or isometries. So how does that read? If you take, this is the rotation invariance theorem, if you take the model, the critical model on a very small fine meshed lattice here, and you take any rotation of this same model, you have a distance between these two, and it converges to zero as delta tends to zero. This doesn't tell you that there exists a scaling limit, but it tells you that if there exists a scaling limit, then it is invariant under rotations. It also tells you that any subsequential scaling limit is invariant under rotations. And actually not only rotations, but any isometry of the plane. Okay, and this is a very deep result, which we obtained with Hugo Duminin-Copin, Karol Kozlowski, Dimak Hachun, and Mendes Ulamaha around 5 years ago. So it's a deep result and something that is highly non-trivial. Somehow you do expect that you have these symmetries, these additional symmetries that that occur as you take a scaling limit, but there's no good reason to, I mean, there's no mathematical reason to obtain these. Right. So maybe I should also mention that what you expect is that more than invariance under isometry is that you have conformal. You have invariance under conformal maps. What that means is if you look at the model in a domain, in a finite domain, and you map that domain onto another domain via conformal map, the two limits are the same. So it's a much, isometries are part of conformal maps, but they're not obviously the only ones. So somehow if I think the conjecture that you have invariance under conformal maps comes from the idea that you should have invariance under rotations due to the universality conjecture, for instance, and now we know we have this. You should have invariant under rescaling, under homotheties. This is because it's just a scaling limit, and scaling limits, if they exist, they're clearly scaling variant. And conformal maps locally look like isometries composed with rescalings. So if you also factor in this algebraic mixing, maybe you expect that that you have conformal invariance under all conformal maps coming from these two sort of invariances. So it's not entirely unrelated. We're obtaining here a very strong indication that you have really emerging symmetries in the limit. Okay. I'm not going to have time to explain how you obtain this this theorem. Maybe I should just explain that it's accompanied by a universality result. The two are obtained together. The universality is for a very specific class of graphs. It's essentially what you need to do is you're going to take the square lattice, but you're just going to change a little bit the parameters. You're going to put different parameters for the horizontal and vertical edges, and you're going to tune these parameters as it's written here, which turns out to be the right way of tuning this parameter so you have criticality. So I've just changed a little bit the parameters and obtained a new model that is also critical. And if you believe universality, it should be that these two critical models, they're in the same universality class, so they're close to each other. And indeed, that is the case. This is what's written here. The two models have, if they have scaling limits, they have the same scaling limit. However, this is not a reasonable thing to expect. It's not reasonable that you obtain the same scaling limit if you put the same parameters on the vertical and horizontal edges as if you put a much larger parameter on the horizontal than the vertical edges. So somehow this isn't correct. But if you put a much larger parameter in the horizontal edges, that means horizontal edges are almost always open, vertical edges are almost always closed. So it should be that the clusters start getting dilated in the horizontal direction. So you shouldn't expect them to have the same shape as when you have same parameters for the vertical and horizontal. And the caveat here is that, yes, the two have the same limit if you modify the embedding through a well-chosen linear map. So if you put a well-chosen linear map there, this compensates for this kind of horizontal dilation that I mentioned. And the way to see this is actually to re-embed your graph rather than embedding it as a square lattice, to embed it as a rectangular lattice with the embedding that depends on the parameters that you've chosen. And this embedding is actually what's called an isoradial embedding. And in this second universality theorem tells you that all the embeddings, all the regular isoradial embeddings of the square lattice have the same scaling limits or the same subsequential scaling limits, or just behave the same way in the large scale. So both theorems tell you some sort of invariance of the scaling limit, but they're not, they don't prove that the scaling limits exist. It's just really subsequentially or scale by scale. Maybe I should mention that this isoradial graphs, that they're much more general than what is drawn here. Ulrich, who is there with you, can tell you much more about this and can tell you how you can extend this result of universality to more general isoradial graphs. Basically, any biperiodic isoradial graph will fall into the same category. So that's what I wanted to mention here. Yes, let me finish by saying that this theorem, this rotational invariance theorem, will be used next week, not in the form of FK, but in the form of the six-vertex model, because it can be translated back to the six-vertex model via this correspondence that I've showed you. And we will use it next week to prove that the height function of the six-vertex model in a certain regime of parameters and in the full plane converges to the Gaussian free field. Now, I don't know what you would like me to do. I can stop here, or if there are questions, I can talk a little bit more about the conjectures here, the critical parameters. I don't know. Maybe, what do you think, Trish?
Let me ask everyone. So what would you like to do? Should we stop here and then break for questions? I mean, we're basically at the end. Or do you have any, would you like to see like epsilon more, maybe like 5 to 10 minutes more? Conjectures? Okay, yeah, so I guess, can you maybe explain conjectures to for 5 or 10 minutes more?
Yeah, so maybe let me just start off here by saying that
I just have one question before you move on.
Yeah.
In your theorem, you're writing distance between two percolation configurations, right? And how are you coupling them?
Yes, right. This is I wanted to say. So when you look at, maybe so that you know what I mean by scaling limits and all of these limits. So the right way of looking at this is via the loop representation. So think of a percolation configuration as a collection of loops, which are the interfaces between the primal and the dual clusters, or simply just the contours of clusters. So if you want to understand large configurations, you want to understand the contours of clusters, and namely the contours of large clusters. So you first of all say that two loops like this, two paths in the plane, are close to each other if you can parameterize them by, say, 0, 1, such that they stay close to each other in infinite distance. Okay, so these are two closed loops, but something like, anyway. this is not close to this. Okay, so you're really looking not just at the shape of the loop, but also in the order in which you pass through these um, through the points. Okay, so this is two loops are close together if they're like this. Two families of loops are close together if all the large loops are close to each other. So this family of loops would be close to a family that has a loop that runs maybe like this, and one like this, and one like this. And the smaller loops, you don't really care about them. And you say two measures that produce families of loops are close to each other. So phi distance of phi tilde is smaller than epsilon. If there exists a coupling such that the probability that the distance between the family of loops obtained from phi, let's call this omega, let's call this omega tilde, omega tilde is smaller than epsilon with probability that is larger than 1 minus epsilon. Okay? So this is the way you consider distances between families of loops and then measures on families of loops. All of this is a little bit non-quantitative. You can render everything quantitative if you want, but it doesn't really matter so much. Right. So once you've seen this, and once you understand that what we care about is the shape of the clusters, so their contours, you can, I think, formulate explicitly and rigorously what it means to have a scaling limit, what these two theorems mean here, these two theorems, what exactly they mean, because you have this distance. But I hope it's clear. And I hope it answers your question, and I hope it also tells you how you should think about these models. You really should think about the shapes of the clusters. That's what we care about. And so what we do expect is that here you have a limit. If you take this, you're going to have a limit that the limit is expressed as a family of loops, right? Once we understood that what we care about is loops and families of loops, the limit should be a family of loops, and the family of loops should be CLE kappa, where kappa is this value that I already forgot. I think it was 4 pi over arc cross minus square root of q over 2, I guess, something like this. I wrote it before. Okay, so this is the major conjecture. If you get this, basically you're done. You've got everything you want. You perfectly describe the critical measure. All of this, I mean, if you really want to get this, you should work also in domains where, is this a clear conjecture? Are there questions about this conjecture?
No, seems good. You can carry on.
Okay. If you prove that the limit exists and that this has conformal invariance properties, you're basically there. You basically prove this. It's such a strong requirement that it's relatively easy then to, I think, to obtain CLE kappa. I mean, all of this is science fiction, so it's when I say relatively easy, I mean compare within this range of things. Maybe let me finish by saying that a more physical point of view, like, is to look at the critical exponents of the model. Maybe you don't want to look at really like the families of loops and obtaining the limits of this. Maybe you just want to know how do these different quantities decrease. So here are the standard quantities where you look at critical exponents. Here's the one that we looked at before. It's the probability of having a large cluster in diameter, and it's supposed to have an exponent, which is usually called alpha 1, but for some reason in my slides it's not. And then there are a whole bunch of other critical exponents. And I mentioned here last time the critical exponent for the percolation probability, which is called beta. You expect the percolation probability to take off as you increase p as p minus pc to some power beta. And all of these exponents are supposed to depend on q because you're in different universality classes. So suppose you get this scaling limit result. Which one of these exponents can you derive? And there's work being that was done, but essentially you have good chances of getting these exponents and this one, which I'll touch upon in a minute. But you're not really going to get these guys here. The difference between the exponents in red and the exponents in green are the exponents in red are really about the critical picture, and the ones in green are about the near critical picture, meaning how you move away from criticality. And so if I give you, a priori, if I give you the picture at criticality, if I tell you exactly what this thing is, you probably can compute things like Hausdorff dimensions and so on. So you probably can compute the exponents at criticality, but there's no reason why you should be able to compute the ones near criticality. And so this is where I wanted to get with these scaling relations. I wanted to explain is that there are these scaling relations that I mentioned for Bernoulli and that we derived with Hugo for FK, which show you that actually the near critical, so all these green guys here, and most of the red guys are related to just two exponents. If you know two exponents, you basically know all the others. And these two exponents are the one-arm exponent, this one, and what's called the influence exponent, which in the case of Bernoulli percolation is the four-arm exponent. Let's here focus on non-Bernoulli. Bernoulli is a bit special. So if you know these two exponents, then you basically know all the others through these relations. You know that all the others exist, and here are their values. Okay? So this tells you both of these exponents are exponents that should be derivable from the critical picture. They are. It's been shown that they are. So if you have the limit at criticality, you get these two exponents and you can get all the other exponents. And this is a more maybe simpler or more physical way of looking at the phase transition and the corresponding universality class. Okay, and I'm going to stop here. Thank you.
Let's thank you, Ioan. Are there any questions? No? Any on the online? Okay, well, yeah, let's thank Ioan again for, I know you couldn't be here, but it was a really great set of
I'm
online.
really sorry that I wasn't able to come. Thank you very, very much for organizing and being so understanding with the traveling arrangements. I hope you took something out of this course. I'll send the slides. I don't know if Trish put the link up, but if not, I'll send him the link to some lecture notes, which are a little bit in the spirit of what I've described here. And if there are questions or you want to ask me, please feel free to send me an email or something. Okay, thank you.
Perfect. Thank you very much. So let's thank Ioan again, and also everyone who gave a course or spoke this week.